All right, welcome everyone. My name is Dimitrios Vagenas. I'm the president of the QLD branch of the society. Welcome to everyone to this presentation from Owen. I should thank Lee for arranging everything. I have been 2 months absent and Lee has filled in for that, and Adrian. So thank you for that. And without further ado, I'll pass on to Owen, who's going to talk about the clusterBMA, Bayesian averaging. And Owen is doing a PhD, correct me, Owen, if I'm wrong, on adolescent activity on the brain while they're developing, with Kerry Mengelsen, who a lot of you will know. But he also has an interest in mental health in general, and from his bio, I read that he's quite active. So thank you very much for doing this presentation for Owen.
Awesome. Thank you for the introduction, Dimitrios. Before I get started, I'd like to acknowledge the Ngunnawal, Ngunnawal and Ngambri people as the traditional owners where I am in Canberra. And I'd also like to pay my respect to the Turrbal and Yuggera people as the traditional owners in Brisbane, where a lot of you will be joining from. Wherever we are in Australia, I think it's important to reflect that we're gathered on stolen land and that sovereignty was never ceded. So thank you so much for the introduction and for the invitation to come and speak here today. I'm going to be talking about some work that I've been doing with my PhD supervisors, Kerry Mengelsen, Edgar Santos Fernandez, and Paul Wu. And this is about a Bayesian model averaging method to combine results across multiple different clustering algorithms. So often in situations where we're interested in applying clustering algorithms, we'll find ourselves in a situation where we'll have results from multiple different algorithms, and each of them will be telling us similar kind of plausible things, but they'll have some differences between them. And it can be challenging to know which of them we should use or how we should combine information across them. So in this case, this is a visually busy slide, but I'll just draw your attention to the boundaries between these clusters. So these are clustering individuals based on brain activity in young people. And you'll see that broadly, these 3 algorithms, k-means, hierarchical clustering, and a Gaussian mixture model are in agreement. But particularly at the boundaries between the clusters, we see that there's some disagreement. So in this next slide, I've highlighted here in yellow, these are the individuals for which the 3 algorithms don't agree on how they should be allocated to clusters with the rest of them. And so this can be a challenging situation to know, how should we choose which of the algorithms to use, or what method should we use to combine inference across them. So when we're looking at application of different clustering algorithms, there's a number of different popular options which are used widely, and each of them will be sensitive to and will emphasize different aspects of clustering structure in the data. And following the path of just choosing one best model is often a pretty arbitrary or unclear choice that could, come down to a lot of researcher degrees of freedom and just, aesthetic or arbitrary preferences. And when we choose just one model and go ahead with using results from just one, then the inferences that we're making based on that clustering are not going to be calibrated for the uncertainty that arises by choosing between different candidate models, which might each be offering some useful insight. And by locking ourselves into just one of these methods, we lose the insights that we could be accessing by incorporating information from the other different algorithms. So why don't we combine them? There are a number of different options that are available to combine inference across different clustering results. And today I'm going to be talking about this work that we've been doing to extend Bayesian model averaging to allow it to be used across a number of different clustering algorithms. And I think it has a number of nice features relative to the other options that make it simple and flexible and intuitive. And I hope you'll try it out in your work. So the basics of Bayesian model averaging, sorry, not the basics. So the past work on Bayesian model averaging, there's been limited development in this space for clustering. There's been a couple of examples of work developing Bayesian model averaging for specific types of clustering models, such as within finite mixture models or within naive-based classifiers. But to date, to my knowledge, there's been no implementation of Bayesian model averaging that can incorporate results from multiple different clustering algorithms. Some of the advantages that we get when we look at Bayesian model averaging compared to other approaches within, say, consensus or ensemble clustering is that we can weight the contribution of results from each model, incorporating some measure of model quality or goodness of fit to contribute to how much of an influence it has over the averaged final results. And it gives us this intuitive framework where we can make probabilistic inferences by combining results from multiple models, even when the input models aren't themselves giving probabilistic estimates. And importantly, we can quantify this model-based uncertainty. So the uncertainty that arises when we're choosing between multiple different candidate models, that's typically ignored either when you just choose one model or in other methods for combining clustering solutions. And so that's a really nice feature of this Bayesian model averaging approach, is that we can then be making inferences that are more robust and calibrated for this uncertainty that arises through the selection of between candidate models. The basics of Bayesian model averaging is that we're trying to calculate the posterior estimate of some quantity delta as the sum of that quantity across all models weighted by the posterior model probability for each model. And here, this posterior model probability is calculated as the marginal likelihood or the model evidence for each model multiplied by the prior for each model over the sum of those across all models. So there's a few steps that we need to take here. One is looking at, how do we choose delta in a way that has a consistent meaning across all of the models? And then a really key piece is estimating this posterior model probability, particularly the key piece here being the model evidence. So I'll talk about that. So in previous work for Bayesian model averaging for mixture models, they've used the Bayesian information criterion as a way to approximate the model evidence and to weight the contribution of each model. So this piece that I introduced in the previous slide, the model evidence for each term, it typically involves a difficult or intractable integral, and it's often approximated for many applications. So in this previous work for Gaussian mixture models, there's a natural relationship where the Bayesian information criterion can be used to approximate the likelihood for each term. So here, the Bayesian information criterion in a Gaussian mixture model is defined by this twice the log likelihood term penalized by this model complexity term. And so what they do is they weight each model by exponentiating the Bayesian information criterion, which you can see up here. So just picking apart how the BIC works in this context, we can see that it's driven by this Gaussian mixture model likelihood term, which is a weighting of a mixture of multivariate normals. And here, this multivariate normal expression looks like this. So this is kind of an assault of a lot of different equations, but just trying to draw your attention here to the key piece in this previous work, which is approximated the weighting of each models using the BIC, is really driven by this multivariate Gaussian density, which I'll come back to in a second. So just to make a brief aside, something that we think about in the context of clustering is in terms of assessing the quality or goodness of fit of different models are the ideas of compactness and separation. Where compactness is looking at how closely grouped together the clusters are, and separation being how far apart the clusters are from one another. And cluster internal validation indices are measures of goodness of fit or model quality for clustering models that are often used as a proxy for model quality and often used for the purpose of choosing between different numbers of clusters K. To choose, what the right number of cluster is for a given clustering model. And it's interpreted in a way that's similar to the marginal likelihood or the model evidence. And in this context, the Bayesian information criterion is sometimes used as a cluster internal validation index for this application. And they are typically, so I introduced this a bit early, but they're often driven by these terms measuring compactness of the clusters and separation between clusters. Compared to the BIC, the benefits of some cluster internal validation indices are that they're agnostic to the clustering algorithm that's been used to produce this set of results, and typically they don't require a likelihood term to calculate them. So coming back to how the BIC has been used, we saw before that it's really driven by this multivariate Gaussian density term. So thinking in these terms of compactness and separation, we can understand that the numerator here is pretty much a within cluster sums of squares term, relative to an overall variance term. And so what we tried to do in this work was trying to find alternative tools which are similar to how the BRC has been used, that use these principles of compactness and separation. So in this case, we ended up choosing two internal validation indices, including the Sierra-Benny index, which is looking at a ratio of cluster compactness to separation, and the Kolinsky-Harabash index, which is similar, looking at a ratio of separation to compactness. So it's within cluster sums of squares to a, measure of separation between cluster centers. So what's nice about these is that mathematically and conceptually, they're similar to how the Bayesian information criterion has been used for weighting clustering models. Sorry, nearly knocked off my water bottle. For weighting clustering models in previous work, but they can be used across algorithms which don't have this likelihood term. And another benefit of these two measures that we've selected is that they've been demonstrated on simulated data to have complementary strengths. So in situations where the Sierra-Benny index performs well under particular constraints on simulated clustering data, or performs poorly, the Kolinsky-Harabash index performs well, and vice versa. So in combined, they're a nice combination. So yeah, as I've said, they're conceptually and mathematically similar to the BIC. They can be used across different clustering algorithms without likelihood terms. And that's important for clustering algorithms, for instance, like hierarchical clustering, which is widely used, which doesn't have a likelihood term. So what we do in this work to enable weighting across different algorithms is this new proposed weighting term based on both the Kolinsky-Harabash and the Sierra-Benny indices. So we calculate this unnormalized weight for each algorithm, and then we approximate the posterior model probability for each algorithm by taking the normalized weight across all of the models. And then just to show how this works in the context of the Bayesian model averaging basics that I introduced earlier, if we substitute in this normalized weight for the model evidence and we set the prior probability for each model to be equal as 1 over the number of models, then this is how it's working as kind of, this is just showing how, you know, the likelihood and the prior fit in to show how the normalized weight is working as an approximation of the posterior model probability. So I got this a bit out of order. I was going to talk about this first. So yeah, this is the step of how we've worked on weighting the contribution of each model. Then we also need to think about how we represent the results from each clustering algorithm in a way that's directly comparable. And so I followed the work of Russell and colleagues who also use this BRC approach. So the way that they represent each solution in a way that can be combined is as a similarity matrix. So in the similarity matrix, each cell represents the probability that data points I and J belong to the same cluster in that model. And importantly, for Bayesian model averaging application, this similarity matrix is nice because it's invariant to how the clusters are labeled, and it's also invariant to the number of clusters, which leads to some nice features of this approach, which I'll discuss later. So these are some examples of heat maps of similarity matrices from, you know, a hard clustering algorithm like k-means or hierarchical clustering, where you're either in or out of a cluster, you'll have clean separation like this. Whereas from something like a Gaussian mixture model where you've got soft probabilistic allocation, you'll have, you know, variation between 0 and 1 in terms of how they're allocated. And then the final piece that we had to work on to bring this method together was thinking about, okay, so the steps we've taken so far is that we've got each algorithm, we've represented the results as a similarity matrix, looking at the probability that 2 points are together in a cluster across all clusters. We've done this novel weighting step. And so what we end up with is a consensus matrix, which looks like this. So we've taken a weighted element-wise average of the similarity matrices representing each clustering solution. But now we want to know, okay, how do we get from the clustering solution back to cluster allocations? The way that this has been done in previous work is to use a full linkage hierarchical clustering approach. And so what I was trying to do, thinking about this, is that in previous work, as far as I'd read, no one had thought about looking at probabilistic allocation at the end of this, or looking at uncertainty in allocation. So I spent a long time going down this rabbit hole, trying to figure out, okay, well, if I'm using this full linkage approach, you know, how can I use, for instance, the pairwise probabilities in this similarity matrix? How can I use them to relate to a final cluster allocation probability matrix? But it just wasn't working very well. You know, fundamentally, I was trying to get probabilistic inferences from this hierarchical clustering step, which is non-probabilistic. Like, you know, you cut the tree and the probability of being in a cluster at that cut is 1. And so in the end, this didn't end up being a very good approach, but thankfully I found a really nice solution in the work of Leo Duan and David Dunstan. So this paper, which came out, this paper, which came out in 2021, looked at applications of Bayesian clustering based on distance measures. And at the end of this procedure, they're trying to do a similar thing to what I'm doing here. So they're taking a posterior similarity matrix and coming from that back to cluster allocations. And that works, that uses this method developed by Leo Duan in this paper in 2020 called symmetric simplex matrix factorization. And I don't have a deep understanding of how it works, but Leo Duan and David Dunstan did it for a similar application, and if it was good enough for them, it's good enough for me. But I'll give a bit of a intuition of the input and output, at least, of this process. So to get from to produce what we're trying to do is we're trying to go from a similarity matrix back to an allocation matrix. So we've got this n by n matrix of pairwise probabilities that 2 points belong together in a cluster, and we're trying to get back to a matrix that says what's the probability that point I is in cluster K. So to get to the similarity matrix, what we do is we take a probability allocation, an allocation probability matrix, and multiply it by its transpose. So here in matrix A, each row is, you know, what's the probability that point I is in cluster 1, point I is in cluster 2, etc. We multiply that by its transpose and get this n by n similarity matrix. What we're trying to do with this symmetric simplex matrix factorization is to invert this process. So we give it this consensus matrix, which is the weighted average of the similarity matrix for each model. We put it through this process of symmetric simplex matrix factorization, very fancy word art to hide the fact that I don't really understand the details of how it works. And it gives us these 2 identical matrices where we specify, you know, how many clusters or how many rows we want in this output matrix. And it gives us this allocation matrix at the end. So putting all those pieces together, we have this nice pipeline now where we can give solutions from any clustering algorithm that can be that we then represent as a similarity matrix. We calculate these new weights. We do this element-wise weighted average. And finally, we end up with these nice cluster allocations. So here's an example of what that looks like with some simulated data. So for this simulation study, we generated simulated data where there's 5 clusters with 100 items in each. And you can see there's high separation, medium separation, and low separation data. And I guess, you know, in the real world, you're never going to have data that looks like this. You know, even optimistically, you're going to have data that looks like this, but there's going to be not very clearly well-defined clusters. So what we're demonstrating here is that the uncertainty of model allocation is really becomes more important to account for as your clusters are less and less well separated. So what we did here was we used the same 3 algorithms I discussed earlier. So we used k-means, hierarchical clustering, and a Gaussian mixture model, each to find 5 clusters. And then we put them through the pipeline. And here, what I'm showing is the solutions where we've done the Bayesian model averaging step, and the size of the points here is proportional to the uncertainty of allocation to that cluster. So we can see that when they're well separated, there's very little cluster model-based uncertainty. As they get less well separated, there's more cluster-based model-based uncertainty. And so what this shows is that our method can really nicely capture uncertainty between the models, and then from this point forward, you can then make inferences based on these cluster allocations that takes this model-based uncertainty into account. we did another small simulation study, which you can read about in the preprint. But basically what we wanted to demonstrate here is that this method can incorporate solutions with different numbers of clusters in each, which is a cool feature that isn't widely available in a lot of the other consensus and ensemble clustering methods. So here we can see a solution for some simulated data where there's k-means with 3 clusters. On the right over here, we have hierarchical clustering with 2 clusters. And when we combine them together, we can see it's got a 3-cluster solution with moderate uncertainty in this section where the 2 clusters, where this cluster has been split. And then we can see even higher uncertainty here where the greater degree of uncertainty is related to which other points they're being grouped with. So up here they're grouped, it's a bit small to see, but up here they're grouped with green. And well, I don't know, the color isn't very useful because it switches between the plots, but you can see, up here they're grouped with these guys, and down here they're grouped with those guys. And so there's different levels of uncertainty depending on the way in which the models are disagreeing. So finally, I'll talk about a case study looking at brain data. So here for the first paper in my PhD, I was looking at trying to find clusters of young people based on their resting state brain activity measured by electroencephalography or EEG. And so as I introduced in the first slide, we've got these 3 dimensions, which are principal components calculated from a number of different brain measures. And we've used these 3 different algorithms, which are slightly in disagreement. And, as I highlighted earlier, there's those points that are kind of at the boundaries where the algorithms are not in agreement on how these people should be grouped. So what we do, just to walk you through, this is what the pipeline looks like. The first step is representing each algorithm as a similarity matrix. These are heat maps of those similarity matrices. So you can see when we're using hard clustering algorithms like k-means and hierarchical clustering, it's just 0s or 1s, like they're either together or they're not. Whereas for a soft clustering algorithm like a Gaussian mixture model, there's more variation between 0 and 1 on whether or not the points are together. And then these are the weights calculated based on that term I introduced before. So then we take an element-wise weighted average of these matrices weighted by these approximations of posterior model probability, and then we end up with this consensus matrix. And then we plug this consensus matrix in as the input to symmetric simplex matrix factorization, specify the number of final clusters that we want. And this is the final output that we get here. So yeah, this is pretty nice to demonstrate that, we're able to combine very different solutions. We're able to capture the model-based uncertainty. And we can take that uncertainty forward if we want to, say, use cluster membership as a predictor for further analysis. We can always also use the uncertainty in that cluster allocation to moderate the strength of the inferences we're making based on that cluster membership. So finishing off with a nice meme, it might just seem like, yet another method in a pretty crowded space for combining clustering solutions, but we think that it has a lot of nice features which aren't available through other methods. So it's agnostic to the number of clusters in each solution and the algorithm that's been used to generate it. It gives us this nice intuitive and flexible framework where the contribution of each solution is weighted by model quality. And we can calibrate the inferences that we're making based on model-based uncertainty, which is captured in this approach. So next steps from here, we recently submitted to the journal Statistics in Medicine, and it's under review. And you can see links on my Twitter to the preprint and R package, or you can also scan this QR code. So the R package is available on GitHub, which I'll show in a second, which you can access at this link or scan here. And if you're interested in reading the preprint, it's up on archive. Here's a link shortener, or also you can look on my Twitter for the link, which is pinned at the top. And in terms of future extensions to this work, I guess natural next steps now that the kind of fundamental pieces are in place are, one would be that it would be cool to think about accommodating input from Bayesian clustering methods. So for instance, I think there would be a natural extension where you could use replicates from draws from an MCMC chain and apply the same steps laid out here to the draws from each sample. And possibly also, we've recently implemented the functionality in the R package that you can manually adjust the prior weights that you're assigning to each model. And so it'd be interesting to look at testing out applications of using informative priors. For instance, you might think about penalizing for model complexity, or in a situation where you know that a particular clustering structure is likely to be best, you could manually give it more weight. And I think another interesting way forward in this space would to be looking at different approaches for using internal validation metrics for approximating the posterior model probability. So in this case, we ended up using the Sciabeni and Kolinsky-Harabash indices because they had this clear kind of conceptual and mathematical similarity to what had been done before with the Bayesian information criterion. But I think it would be interesting, you know, if you accept the premise that that's a reasonable approximation, and I think there are analogs to approximate Bayesian computation in terms of using summary statistics in place of the likelihood, then it would be interesting to look at, you know, well, what about other internal validation metrics? And we talk about this a bit in the paper as well. So yeah, thank you so much for listening to my talk. Just briefly before I stop, I will stop sharing my screen and then I'll reshare so you can have a look at, oops, this. So this is, if you're interested in playing around with the package, you can have a look. It's all available on my GitHub. And there's instructions here for installing it and a bit of a demo vignette, which you can run through. I was planning to, I'd prepared some nice demo code to show you a live demonstration of stepping through. However, today I got an email from someone who said, oh, I tried installing your package and I really want to try and use it. I'm getting this error. Can you like help me troubleshoot my way through it? So I was like, okay, I'll try. Oh, so I uninstalled it, reinstalled, and now I'm getting the same error as them. I really should have waited until after this talk, given that it's bricked my installation, but hopefully I'll fix that in the next day or so. I think there's a Python, some random dependency in Python that's been updated that's causing some errors. So hopefully that'll be fixed by the time you try it out. I'll try and fix it tonight or tomorrow. But yeah, there's all the information here on how to set up a content environment which has the relevant versions of Python and TensorFlow, which are needed to do the matrix factorization step. And you can also find our preprint on arXiv. But yeah, this is my first time publishing an R package, and I'm really keen to, you know, have conversations with people about does it work on your system? I suspect given today's experience, it currently won't work on your system. But once I fix that, I'm also interested to know, you know, get some feedback on stress testing and ask people to help break it and figure out what might make it more useful. But yeah, thank you so much for listening. I appreciate it. Appreciate the opportunity to speak here today.
Thank you very much, Owen. Where am I? Yeah. And now, does anyone have any questions? Yeah, Adrian.
Thank you, Owen. Really nice stuff. So your simulations and also the example data set, like the data was quite scattered, like somebody had dropped a whole load of Smarties, but often data I see has still got some correlation in it. So you can get, even in like in 2 dimensions or 3 dimensions, you know, strong shapes like curves and other weird sort of splatters or triangles, you know. So I was trying to think of trying to break here and trying to think of a shape that would be particularly bad. Like what about like an X, two strongly correlated, one negatively and one positively? What would it do with an X?
Yeah, my intuition is that would probably come more down to the individual clustering algorithms that you're using. I think the clustering thing that comes to mind for me, I'll just see if I can bring it up and share my screen. Yeah, this one. So there's this documentation for scikit-learn, which shows like, you know, how different clustering algorithms perform with different types of data and weird correlation structures. So I think, you know, Bayesian model averaging isn't a magic wand. It can't fix. And I talk about this in the paper as well. I think that, you know, it's important to keep in mind that there's garbage in, garbage out. Like, you're not going to get a better solution by averaging 2 crap solutions, and you're not going to get more insight by averaging a good solution and a crap solution. So I think that, you know, it's still, with the application of any clustering algorithm, you know, the onus really remains on the analyst to make sure that you're getting sensible, useful insights, and that you're combining inferences across things that you want to share. So, you know, for instance, in this case, if you had like a weird correlation structure, like, I don't know, these guys over here, like maybe you would get a little bit of disagreement between DB scan and optics, for instance, but you probably wouldn't want to average optics with the Gaussian mixture model, because the Gaussian mixture model is obviously doing a crap job. So, yeah, no, I think it highlights that you don't want to, you want to do, it doesn't free you of your responsibility to still do a lot of quality assurance and checking along the process, and make sure that you're putting good quality results in, that it makes sense to average across. I don't know if that answers your question.
Yeah, look, that picture's really nice. I like that. They were the kind of weird shapes I was thinking of. Yeah, so but I suppose I'm worried about people using it and not doing that. Just, you know, you see a lot of people just get the data, feed it through an algorithm, and then get the result and not. So have you got warnings in your, or do plots like that? I suppose the plots like that appear, and hopefully somebody would see that it was an issue.
Yeah, I think that possibly it's a good point, and I think, you know, we'll consider adding more explicit warnings in the output. I think there definitely is scope for kind of less critical use of it, to kind of plug stuff in and go, oh, nice, like it's averaged across models, so it's going to be better, sort of thing. So maybe I should actually have those explicitly come out as like, make sure you're not feeding crap in here, sort of thing, and that it's your responsibility to do that along the way. I've tried to put that into the paper a little bit, but I think that's a great idea to actually put it in the R package, so that for the sort of people who just might blunter in and assume that it's going to magically give them good stuff, I think that would be a good idea to remind them that they still got to do their basic homework and due diligence as a first step.
Anyone else has any other questions? Owen, can I ask something? I might have missed it, but have you compared your algorithm against other algorithms who could do the same job in similar problems? You are muted.
Sorry. Yeah, I'm not aware of other algorithms who can do specifically what we're trying to do.
But could you fit your algorithm into a problem that? So, what I'm getting at that you have internally benchmarked it with simulated data.
Yeah.
But is there somehow that you could benchmark it external, like tell me that my algorithm in this problem that this guy solved, which might be a specific problem for your algorithm that you can use it, does the same or better job?
Yeah. So we haven't included anything like that in the paper. I think that there are some natural examples which, depending on what reviewers come back with, or it's the sort of thing that I might add iteratively to the GitHub repo as well. One thing that comes to mind in answer to that is the case of model averaging for Gaussian mixture models. So, you know, I spoke about in this previous work, they've done it for Gaussian mixture models, and they've used the Bayesian information criterion to approximate. So I think what I've found through my own, I haven't written up these results, but I've played around using my method and comparing it to their method, where I'm just averaging Gaussian mixture models. What I've found is that what I see to be a strength of our approach is that, maybe I'll bring up my slides again so I can illustrate what I'm talking about. Sorry, just one second. So I'll just go back to, so in this previous work where they've used the Bayesian information criterion, here, this one. This one. So they exponentiate the Bayesian information criterion to develop their approximation for the posterior model probability, which makes sense because, you know, they're doing the inverse of how the BIC is defined with relation to this likelihood term. But that exponentiation step actually means that if there's even a tiny difference in the BIC between models, the weighting massively gets inflated to the one with the slightly better BIC. And so compared to their method for weighting, when you use our method based on the Sciabeni and Kalinsky-Harabash, it's much less likely to give, you know, I found that if there's even a tiny difference in model performance between, you know, one Gaussian mixture model and another, they'll give 95% of the weight to the one that's marginally better according to the BIC. Whereas the distribution of weight is more moderate, I guess, using our weighting. So that's the only example where I've informally done some benchmarking and looking at it on my own time. But I think you're right that it would strengthen the work to have some more benchmarking of, this consensus algorithm can do ABC. Here's what it looks like if we use our approach. I agree that would be a strength.
Thank you for that. The second question, how computationally intensive is your method? Like, can it be run on a laptop or on a desktop? Is there any parallelization or no?
Yeah, I've run all this on my laptop. I haven't had any need to use any high performance computing or anything. The most intensive part of it is the matrix factorization step, which uses TensorFlow. And that's what I've been wrangling with in this Python version control stuff that broke and unfortunately cut my demo short today. But yeah, that takes, in the instances I've been working with where I'm looking at, 3 to 5 clustering models with, of the order of a few thousand points or whatever, it takes like 1 minute to run on my laptop. So not very computationally intensive. I think that considerations around parallelization or high performance computing would become relevant if you're trying to do this method with fully Bayesian clustering results and having, a lot of draws from an MCMC chain or something like that as what you were trying to average across. But for now, it's pretty quick with the sort of methods that I've been looking at.
All right, thank you. Any other questions, guys? Remarks? No? Well, in that case, thank you very much, Owen. Yeah,